During Chapter 2, we specifically talked about the differences between physical changes and chemical changes. The main difference is that in a chemical change, the composition of our substance changes. In this chapter, instead of calling them chemical changes, we're going to call them chemical reactions, and we can abbreviate that with RxN. We show chemical reactions with something called a chemical equation, where we write our reactants, anything that we start with, on the left side of the arrow, and on the right side of the arrow we have our products. Those are the new things that we have made. So for this example, I have carbon plus O2, or oxygen, and they're combining to form or to yield carbon dioxide. So this arrow is not read as equals because it's not an equal sign, because carbon by itself and oxygen by itself are very different from carbon dioxide. It's just showing that these things form or yield this compound. So whenever a chemical reaction occurs, the law of conservation of mass has to be followed, which says that matter cannot be created nor destroyed. So I can't magically make some oxygen atoms appear, and I can't make oxygen atoms disappear either. But mass or matter can change locations. So for this example, I have H2 plus O2, or hydrogen plus oxygen, yielding or forming or producing water, or H2O. So what this says right here in green so far is that you start with 2 atoms of hydrogen and 2 atoms of oxygen, and at the end you end up with 2 atoms of hydrogen and only 1 atom of oxygen. That can't happen. I can't start with 2 atoms of oxygen and only end up with 1. That means that I made 1 disappear. We're not magic. We can't do that. So we have to use these 2 rules to make sure that this does make sense, because right now we say that that is unbalanced. So I cannot change the subscripts here. I cannot just add a 2 here after the O and everything be okay, because H2O and H2O2 are different compounds. H2O is water. H2O2 is hydrogen peroxide. We wouldn't want to drink hydrogen peroxide. They are different compounds, so I can't change the subscripts. But I can use something called coefficients. Coefficients are large numbers that go in front of either the element, as I have over here, or in front of the compound. So I'll show you how that works. So I have 2 oxygens on the reactant side of the arrow, but I only have 1 over here. So what I do is I put a number 2 in front of H2O. So what that means is I now have 2 oxygens. It's kind of like in math class where the coefficient gets distributed to everything that's after it. So the 2 gets distributed to this one and distributed to that imaginary 1 that we have after the O. So there are 2 oxygens here, which is great, but you can easily see we have a problem, because now I have 2 times 2, I have 4 hydrogens on this side. But that's okay, because I can make there be 4 on this side too by just adding a coefficient of 2 in front of the hydrogen. So now I have 4 hydrogens on this side, 4 hydrogens on this side, 2 hydrogens on the reactant side, and 2 oxygens on the reactant side, and 2 oxygens on the product side. So now we say that this is balanced by using coefficients. Just a side note, I don't just have H by itself here or O by itself here. I had to have H2 and O2. That's because those are some of our diatomic molecules that we briefly talked about in Chapter 6. The elements that always have to have that little 2 after it are hydrogen, nitrogen, oxygen, and everything in the F column. Now I know that says F row here. That's because a tricky way or a sneaky way of remembering that is with little rhymes, which is H, no, F row. So any of those have to have that 2 after it in the equation. So here are some more examples for you. If you want, go ahead and pause it and write these down and try them on your own. If you're not comfortable doing that yet, just follow along with me. So at the beginning here, I have 1 potassium and 2 bromines. And at the end, I have 1 potassium and only 1 bromine. That's unbalanced. So to get 2 bromines on this side as well, I need to use a coefficient of 2. Now I can't put that 2 in between the K and the Br. The 2 has to go in front of that whole chunk. So I have to put a 2 here, which solves my bromine problem. I have 2 and I have 2. But now I have 2 potassiums on this side and I only have 1 over here. That's easily fixed by adding a 2 in front. So I check 2 potassiums, 2 potassiums, 2 bromines, 2 bromines, everything's good. Our next one, I have 2 hydrogens, 2 chlorines on my reactant side. On the product side, I only have 1 hydrogen and 1 chlorine. So if I want to fix that, I can just put a 2 there. So I see I have 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines, and that one was fixed with just 1 coefficient. Okay, for this one, I have H2O2 hydrogen peroxide breaking down into water and oxygen. So I have 2 hydrogens, that's good, but oxygen, I have 2 oxygens and I have 3 on this side. So I can't do that because that means that I'm making an oxygen and that is impossible. So what I'm going to do is I'm going to put a 2 right here, which seems kind of weird, but I've had a lot of practice at this. Once you have practiced several of these, you'll be able to start to kind of see the patterns of how to figure these out. So if I put a 2 here, I have 2 oxygens here, and I have 2 oxygens here. So I have 4 on this whole side. I want to have 4 on this side, so I'm going to put a 2 right here. So now I have 2 times 2 to give me my 4 oxygens, which is great. Let's check those hydrogens though. So I have 2 times 2 hydrogens, and then I have 2 times 2 hydrogens here as well to give me 4, so that is balanced. Our last one here, I have 2 nitrogens and only 1 nitrogen here. I have 2 hydrogens and 3 hydrogens here, so both of them are not balanced. So I'm going to balance the nitrogens first. So if I want 2 nitrogens on this side as well, I'm going to put a coefficient of 2 there. So that's fixed, but now my hydrogens are not, and they weren't before either. So I have 2 times 3 hydrogens to give me 6. If I want there to be 6 here and I already have 2, then I put a 3 here. So something important to notice is that I've used a lot of 2's here, but I could use a 3, a 4, a 5, a 6, a 7, 8, whatever it takes to make sure that everything is balanced, which it is. 2 nitrogens, 6 hydrogens, 6 hydrogens. Okay, so mass has to be conserved, but so does energy. So energy also cannot be created nor destroyed, but it can change locations. So if we look at that equation that we just did, the nitrogen plus hydrogen creating ammonia, or NH3, how that works is N2 would be 2 nitrogens bonded together. 3 H2s would be, this is 1 H2, this is another, and then here I have 2 NH3s, so this is 1 NH3, and this is another NH3. So to make these things become this, I have to break the bonds that are between these atoms, and then those atoms are going to rearrange in this form. So to break those bonds, I have to put energy in to break them. When they form, energy ends up being released, but sometimes I have an overall absorption of energy, meaning I need to put a lot of energy in to make these things become this. And sometimes a lot of energy gets released from that chemical reaction. So an exothermic reaction, we've seen that word before. Exo means exit. Energy is leaving. It's being released. And in this case, it's being released to the surroundings. So conservation of energy is still happening here. The energy didn't disappear. It's just in a different location. Instead of being trapped in those bonds, it's been released to the surroundings near the reaction. So if I look at this picture here, I see that my reactants start with a certain amount of energy, and then the energy increases and then it decreases. So my products have less energy than my reactants did. And that makes sense because there was a release of energy. So down here I have the energy of my products. Well, where did this amount of energy go from here to here? That energy went to the surroundings. We noticed that it wasn't just a straight line down. There's this hill here. we call that the activation energy. That's how much energy you have to put in to break the bonds of your reactants, or what you started with. So some reactions have a very small hill, meaning you don't have to put much energy in at all to get the reaction started. Some reactions have a large amount of activation energy, so you have to put a lot of energy in to get it started. So this is all what we call exothermic. Endothermic, so endo, inside, energy is being brought in or it's being absorbed from the surroundings. So the way this works is the opposite of what I had here. So I have reactants toward the bottom, and my products actually have more energy because that energy has been absorbed. So the reactants are going to get that energy from the surroundings, or it's going to pull it in. And notice that the hill for this one is much, much larger. So I have to put a lot of energy in order to make an endothermic reaction occur. And then lastly, we can affect how quickly a reaction happens, and that's called that reaction's reaction rate. Rate is another word for speed. So this is just how fast I can get those reactants that I started with to turn into the products, the new stuff. The more collisions there are between the reaction or the reactants, the faster the reaction will occur. So if I want to make a reaction happen faster, I can increase the stirring. So like if I put two things together and I just let them sit, it will react at a certain rate. But if I stir them together and I increase those collisions, it will happen faster. Same thing if I increase the temperature. If I increase the temperature, I'm increasing the kinetic energy, and that means I increase the amount of movement they have, and they're increasing their collisions. So the faster, at the higher temperature it happens at, the faster the reaction will occur. You can also increase the amounts that you have for your reactants. So instead of using 5 milliliters of vinegar, maybe you use 10 milliliters of vinegar. That will make it happen faster. And then lastly, you can add what we call a catalyst. A catalyst is going to lower the activation energy. So instead of our hill being this big, maybe the activation energy makes it only this big. So you don't have to put as much energy in to make the reaction get started. However, that catalyst doesn't actually participate in the reaction. So we wouldn't include it in our equation when we write out our reactants and our products and we make it all balanced. But it does help to make it happen faster.